Our planet, Earth, is a miracle of cosmic proportions. It floats in the vast expanse of space, a blue and green gem that stands out against the dark void. From the perspective of the moon, Earth looks serene and fragile, a rotating sphere that harbors an incredible array of life forms. It's a vibrant oasis teeming with life, from the dense forests filled with diverse wildlife to the colorful coral reefs bustling with fish. The lush rainforests are home to countless species, each playing a unique role in the intricate web of life. These stunning landscapes, with their towering mountains, flowing rivers, and grand canyons, are a testament to the universe's ability to create complexity and beauty. The colorful coral reefs, with their myriad of marine life, showcase the diversity and resilience of life on Earth. But have you ever wondered how this incredible planet came to be? How did the night sky, filled with countless stars, influence the formation of our world? What cosmic events led to the creation of this haven for life? How did a swirling cloud of gas and dust give rise to the world we call home? This cloud, known as a nebula, was the birthplace of our solar system. Over millions of years, gravity pulled the gas and dust together, forming a protoplanetary disk around a young star. This is the story of Earth's birth, a cosmic journey spanning billions of years. From the formation of galaxies to the birth of stars, the universe has been in a constant state of flux, shaping and reshaping itself over unimaginable timescales. This journey is filled with fiery collisions, dramatic transformations, and ultimately, the emergence of life itself. Meteor impacts and volcanic eruptions played a crucial role in shaping the early Earth, creating the conditions necessary for life to begin. We will delve into the heart of a collapsing nebula, where stars are born and planets begin to form. These star-forming regions are the cradles of new solar systems, each with the potential to harbor life. Witness the formation of our solar system, as planets coalesce from the dust and gas surrounding a young star. This process, known as accretion, is a delicate dance of cosmic forces that ultimately led to the creation of Earth. Trace the incredible journey of Earth from a molten inferno to a cradle of life. In its early days, Earth was a hostile, volcanic landscape, but over time it cooled and water began to accumulate, setting the stage for the emergence of life. Join us as we unravel the mysteries of our planet's past. Through the eyes of scientists and the lens of modern technology, we will explore the key events that shaped Earth and made it the unique world it is today. Gain a newfound appreciation for the delicate balance of cosmic forces that allowed our world and life itself to exist. From the precise alignment of planets to the intricate interplay of gravitational forces, every element of our solar system plays a crucial role in maintaining the conditions necessary for life. Our story begins not on Earth but in the vast expanse of space within a giant cloud of gas and dust known as a nebula. These nebulae are the birthplaces of stars, cosmic nurseries where gravity pulls matter together, igniting nuclear fusion and giving birth to brilliant shining stars. Imagine a cold, dark cloud of hydrogen, helium, and heavier elements forged in the hearts of long-dead stars. This cloud, our cosmic cradle, drifted through the Milky Way, a silent giant holding the ingredients for our solar system. These nebulae are not static entities, they are dynamic, swirling masses of gas and dust, constantly in motion due to the gravitational pull of their own mass. It is within these turbulent clouds that the seeds of planets, stars, and even life itself are sown. About 4.6 billion years ago, something extraordinary happened in our corner of the Milky Way. This event set the stage for the birth of our solar system, a process that would take millions of years to unfold. A nearby star exploded in a supernova, sending shockwaves through our nebula, disrupting its delicate balance. This explosion was so powerful that it sent ripples through the vast cloud of gas and dust, triggering a series of events that would eventually lead to the formation of our sun and planets. This disturbance caused the cloud to collapse in on itself, pulled together by the irresistible force of gravity. As the cloud contracted, it began to heat up, and the particles within it started to move more rapidly, colliding and sticking together. As the cloud contracted, it began to spin faster and faster, like a figure skater pulling in their arms. This increase in rotational speed caused the cloud to flatten into a disc shape, with most of the material being pulled toward the center. This spinning motion flattened the cloud into a swirling disk of gas and dust, with a protostar, our nascent sun, at its center. The protostar continued to gather mass, growing hotter and denser, eventually igniting nuclear fusion in its core. This process, known as the nebular hypothesis, is the foundation of our understanding of how solar systems form. It explains not only the formation of our sun but also the creation of the planets, moons, and other celestial bodies that orbit it. Within this protoplanetary disk, tiny grains of dust, remnants of ancient stars, collided and stuck together. Over time, these grains formed larger and larger clumps, eventually becoming planetesimals, the building blocks of planets. These clumps, held together by static electricity, marked the very beginning of planet formation. As they continued to collide and merge, they grew into protoplanets, which would eventually become the planets we know today. This incredible journey from a cloud of gas and dust to a fully formed solar system is a testament to the power of gravity and the dynamic processes that shape our universe. Over millions of years, these tiny dust particles continued to collide and stick together, a process known as accretion. As these clumps grew larger, their gravitational pull increased, attracting more and more material from the surrounding disk. In the region where Earth would eventually form, these growing clumps of rock and metal, called planetesimals, orbited the young sun in a chaotic dance, colliding and merging, gradually increasing in size. These collisions were not gentle encounters. They were cataclysmic events that released enormous amounts of energy, heating the young planet. Over time, a dominant planetesimal emerged in Earth's orbital path, sweeping up the remaining debris and further increasing its mass. This protoplanet, still a far cry from the Earth we know today, would continue to evolve and transform through a series of dramatic events. Section 5. The Iron Catastrophe, Differentiation, and Earth's Layers. As the young Earth continued to accrete material, temperatures within its core soared, melting rock and metal. This melting was a pivotal moment in Earth's history, leading to a process known as differentiation. During differentiation, the denser materials, primarily iron and nickel, sank towards the center of the planet, forming Earth's core. The lighter materials, such as silicates, rose to the surface, forming the planet's mantle and crust. This separation of materials into distinct layers is what gives Earth its internal structure, a key factor in its habitability. This period of intense heat and differentiation, known as the Iron Catastrophe, was a time of great upheaval. The young Earth was a molten inferno, its surface a sea of liquid rock. Yet from this chaos, order began to emerge. Section 6. A Molten Inferno. Early Earth's Violent Past. The early Earth was a place of unimaginable violence. The planet's surface was a seething cauldron of molten rock and lava, constantly reshaped by relentless volcanic activity. Volcanic eruptions spewed molten rock into the atmosphere, creating vast clouds of ash that darkened the skies and altered the climate. Meanwhile, asteroids and comets bombarded the surface, leaving behind massive craters and causing widespread devastation. These impacts were not just destructive, they were also transformative. These impacts delivered water and other volatile compounds to the young planet, essential ingredients that would later contribute to the formation of oceans and the development of life. Over millions of years, these cataclysmic events played a crucial role in shaping Earth's future environment, setting the stage for the planet's evolution. The atmosphere of early Earth was a toxic mix of gases devoid of free oxygen. It was composed mainly of carbon dioxide, methane, ammonia, and other noxious gases. It was a hostile environment, inhospitable to life as we know it. The surface was barren, with extreme volcanic terrain and constant geological upheaval. Yet beneath the surface, in the depths of the newly formed oceans, a different story was unfolding. The oceans were a crucible of chemical reactions, driven by undersea volcanic activity. In these dark, mysterious waters, the building blocks of life were beginning to assemble. Simple organic molecules formed, setting the stage for the emergence of more complex compounds. This period of intense bombardment, known as the Late Heavy Bombardment, was a defining era in Earth's history. It was marked by frequent and massive asteroid collisions. These impacts had a profound impact on the evolution of Earth and other terrestrial planets. They reshaped the surfaces, creating vast basins and mountain ranges. It shaped the surfaces of these planets, leaving behind a record of their violent past, etched in the form of craters and geological formations. These celestial collisions delivered essential ingredients for life, such as water, carbon, and other vital elements, scattering them across the planet's surface, and may have even played a role in the emergence of life itself. The combination of these elements and the energy from these impacts could could have sparked the chemical reactions necessary for life to begin. Section 7. A cosmic collision, the birth of our moon. One of the most dramatic events in Earth's early history was the formation of our moon. While there are several theories about how the moon formed, the most widely accepted is the giant impact hypothesis. This hypothesis suggests that a Mars-sized object named Theia collided with the young Earth billions of years ago. The impact was cataclysmic, ejecting a vast amount of debris into space. This debris, bound by gravity, coalesced over time to form our moon. The formation of the moon had a profound impact on Earth. It stabilized Earth's axial tilt, creating the seasons we experience today. The moon's gravitational pull also creates tides, which play a crucial role in regulating Earth's climate and influencing the evolution of life. Section 8. Oceans of liquid rock, the formation of Earth's crust. As Earth cooled, its molten surface began to solidify, forming the first crust. This crust, however, was not the stable, solid ground we know today. It was constantly being reshaped by volcanic activity and bombarded by asteroids. Over time, lighter materials continued to rise from the mantle through volcanic eruptions, gradually forming the continents. The first continents were small and scattered, but over billions of years, they collided and merged, forming the larger landmasses we see today. The formation of continents was a crucial step in Earth's journey towards habitability. Continents provide landmass for life to evolve on, and their weathering processes deliver essential nutrients to the oceans.